All right, thank you. I'd like to thank you all for coming to the session today. And yeah, I'll be talking about some of the work we've been doing at AER to model the chemistry of these smoke plumes in the first few hours after emission and how to incorporate the small scale process into larger scale and global scale models. And I'd like to thank all of my co-authors and thank NSF for funding the project. So, as we all know, biomass burning is a large source of gases and particles to the atmosphere, and understanding the impacts of biomass burning is made difficult because the emissions can be highly variable between fires. As we saw before, about half of the organic compounds in the smoke can be unidentified, which are a mixture of semi-volatile, low volatility, and extremely low volatility compounds I'm just going to collectively refer to as SVOCs for this talk. In addition, there's rapid chemistry that takes place shortly after the emission of the smoke that produces secondary pollutants like secondary organic aerosol, ozone, and peroxyacetyl nitrate, or PAN. And so understanding this chemistry is critical to understanding the air quality and climate impacts of biomass burning. Now, the tool I use to study these processes is the Aerosol Simulation Program, or ASP, which we designed specifically to study the formation of ozone and evolution of organic aerosol and smoke plumes. For the gas phase chemistry, for compounds with 4 carbons or less, it's based on the Leeds master chemical mechanism, whereas for larger compounds, we use the lumped chemistry of Rackham-2. It includes modules for aerosol thermodynamics, and the organic thermodynamics is based on the volatility basis set. It also has routines that calculate the aerosol size distribution and optical property evolution. Now, in this talk, I'm mainly going to be showing results using the model as a simple Lagrangian box model, diluting with time. But you can also implement the same model into a 3D model, which is what I'm showing here on the right, where we did simulations of sulfate and organic carbon formation in a South African plume using a cloud resolving model. So what I'd like to show today first is some results we've gotten studying the Williams fire in California, which was from a paper by Akagi et al. And this is a really nice case study to look at because first, the skies were clear all day, so we really don't have to worry about clouds impacting our photolysis rates. The relative humidity was low, so we don't really have to worry about aqueous chemistry. And the smoke plume was relatively isolated from other pollution sources, as you can see in the figure here. Now, the Twin Otter sampled the plume several times, as you can see in the map down here, and the instruments included the University of Montana Airborne FTIR system for gas phase measurements, and a compact time of flight AMS and SP2 for aerosol composition. Now, the main results from this study was that there was significant chemical formation of ozone and PAN, but when corrected to CO, the organic aerosol actually had a slight loss as the plume moved downwind, and that's what we're going to try to explain with our modeling study. So to start with, I did the model run just using the compounds we had identified either from literature emission factors or from the measurements themselves, and assuming that the unidentified compounds are unreactive for the moment, just to give us a baseline of the model performance. These are results for ozone and PAN, both corrected to CO, and this CO2, it's a little hard to see. The data points here, the horizontal error bars are the uncertainty in the smoke age due to the uncertainty and variability in the horizontal wind. The different curves here are different model results. The different colors correspond to a different assumed dilution rates based on the observed dilution of CO. The different types of line correspond to the fact that we don't know exactly where in the plume the aircraft was sampling. So we have solid lines for right through the middle level photolysis rates, and then the dashed and dotted correspond to the enhanced photolysis rates at the top and reduced at the bottom. So what we can see is that the model generally gets this secondary formation of ozone and PAN correct, but it is overestimating the values downwind. Now, when we look at organic aerosol, the error bars are about 36% on the measurement, but we can see that without including the chemistry of SVOCs, we are slightly underestimating the organic aerosol formation downwind. In addition, there are a lot of other VOC compounds, like acetic acid I'm showing here, where we see clear production in the smoke plume, but we don't have any of that production reflected in the model. And so what we wanted to explore was, could we explain this by adding reasonable chemistry for these unidentified SVOC compounds. So the first thing we did was use sort of the standard chemistry for the volatility basis set, where you have these SVOC compounds react with OH with an OH reaction rate that varies depending on which literature study you're using, and produces a lower volatility compound, and how much lower the volatility is depends also on what paper you look at. So we got a few different studies of and implementations, of this mechanism, and those are what I'm showing here in the gray and the brown bars with the corresponding OH reaction rates and volatility reductions there. And you can see that for these literature estimates, they can dramatically overestimate the amount of organic aerosol formed, generally because of the fast OH reaction rate. These fast OH reaction rates also lead to a sink of Hox radicals, which generally suppresses the ozone formation in the plume as well. Of these, the best match is the brown case, where we get reasonable results for ozone with this OH reaction rate, but we're still overestimating the organic aerosol formation by about a factor of 2. So what we wanted to see is if we took the chemistry one step further, still very simplified, but allowing these SVOCs to act more like we expect organic compounds to react, could we get a better match? And so in this case, we have an SVOC reacting with OH to form a peroxy radical. And when that peroxy radical reacts with NO, it can form a lower volatility compound. However, it can also break apart, making a higher volatility but still semi-volatile compound and a VOC fragment. In addition, this reaction should form NO2 and HO2, and that should lead to further ozone formation. And this formation of HO2 leads to a regeneration of the Hox radicals that wasn't present in the first scheme. So here I'm showing the organic aerosol results again. I've added 2 bars to the end. The brown bar again is our low OH reaction rate, which is roughly consistent with what you would get from Rackham-2 if you had a long chain alkane. Now if we stick with that same reaction rate but assume that 50% of the peroxy radicals fragment, we get the purple bar, which is in pretty good agreement with the observations. Now with that fragmentation pathway, we would expect 1 carbon, 2 carbon compounds to be spitting off as well. So in this case, if we assume that that VOC fragment is acetic acid, we get the results shown here, which is a remarkably good match, probably better than it should be. So we're not saying we've definitively shown what the source of acetic acid is. We're just saying that this fragmentation pathway is not only consistent with the organic aerosol observations, but it also provides a pathway for forming these smaller compounds further downwind. Now, the next step was to think about the NOx and Hox chemistry of these SVOCs. Now, the purple case basically ignores that, and what you can see is that that leads to an overestimate of NOx downwind, although it's still within the upper end of the uncertainty range. We first tried simulating the SVOC chemistry, assuming it was just like a long chain alkane. This generally produced too much ozone and pan. So we started playing around with the numbers to preserve our match with organic aerosol, pan, and ozone while trying to prove our match with NOx. And this is the best we got, but as you can see, whereas here we were at the high end of the uncertainty bars, now we're at the low end of the uncertainty bars. And while we would have liked to have seen a change that would have put us right through the center of the cloud for ethylene, suggesting we're getting the OH right, we're really not seeing any change there. So it's a bit of a whack-a-mole thing, but I think we have an improved simulation of the chemistry by taking these compounds seriously, but it's by far not perfect yet. So I just wanted to also take a few minutes to talk about how we're trying to use this model to parameterize this subgrid scale chemistry into larger scale models. So we're working with Catherine Travis over at Harvard to implement a parameterization into GeosChem, following the approach that was used by Vinken et al. For ship plumes, where we use the plume model to develop lookup tables of the formation of ozone, pan, organic aerosol, and whatever other species we're interested in versus smoke age, with dependence on the biome, the temperature, the solar zenith angle, and whatever other fire and meteorological parameters turn out to be important. So I'm just quickly going to show some results, early results from this. On the left, we have ozone formation for savanna and grassland fires, where the different lines correspond to different temperatures. And the right is for boreal forests. This kink is because we're only the lookup tables only contain the data every hour. But what you can see is that the savanna fires, where you have a lot of NOx relative to your VOCs, you do get significant ozone production, and it goes up quite a bit as temperature goes up. For the boreal forests, most of the chemistry is done within the first hour, and you get a much lower ozone production downwind. You can also see this if you look at how the NOI species partition in the model downwind. They start out mostly as NOx, which is the yellow here. You can see in the boreal forest that quickly reacts into pan in the green, other peroxynitrates, other alkyl nitrates, and particle nitrate, suggesting that that little bit of ozone formation we got from the boreal fires is really going to be it until the pan starts breaking apart much further downwind. Whereas with the savanna and grasslands, even though we've made a lot of ozone, we still have 50% of the NOI as NOx, allowing that chemistry to continue going on past those first couple hours. I think, do I have time? I think I'll skip this one. But just to go over our conclusions, the chemistry of these unidentified compounds impacts not just the organic aerosol formation, but also the ozone, NOx, and pan formation within the smoke plume. And we've shown that with reasonable values for this chemistry, we can get a pretty good match with these observations within the Williams fire, but we're still having some issues with OH. And our hope is to apply this method to many more fire data sets to give us a sense of what are the differences between the smoke plumes where you have significant organic aerosol formation and those where you don't, and try to get some common chemical markers out of them to let us know ahead of time which fire we would expect from a given burn. So here's our future work, more data. And we're also working with John Lynn's group at the University of Utah to put this model into the STILT-Chem dispersion model so that we can see what the impacts of this chemistry are on specific receptor locations. And with that, I'll stop. And thank you very much.
So we do have time for a couple of questions. A lot of time if no one wants coffee, but let's break.
Not that much time, no.
Let's break in a couple minutes. Are there any questions for Matt?